Our final speaker before the break is Hong Jin, who is a graduate student at the Department of Agriculture and Biosystems Engineering at South Dakota State University. And he's going to talk about carbon materials from DDGS, assuming that I can get his PowerPoint pulled up, which has been problematic today. Okay, this is Jin. There we go.
Good afternoon, everybody. Today I'm going to talk about the carbon materials from DDGS. DDGS means distillers dried grains with cellulose for supercapacitors and properties improvement by hydrogen peroxide surface modification. And I'm Hong Jin from South Dakota State University. Now let's take a look at the contents which I'm going to talk about. First, I will give you a brief introduction of supercapacitors, and then what kind of carbon materials we will use for the supercapacitors. And I will give you some characterizations we get from our active carbon and modified active carbon. And also give you electrochemical properties, which I got from the results, and then finally give you a summary. Supercapacitors is based on the capacitors theory, which developed for about 100 years ago. And technically, there are two kinds of supercapacitors. The first one is called double layer capacitors. It's based on the double layer theories. Traditionally, it's developed by Helmholtz for probably 20 years ago. And another one is called pseudocapacitors. It's kind of like of secondary battery because there's a reaction in the system. And people combine these two capacitors together. We call the third capacitors hybrid capacitors. It's kind of combine this together. We use porous materials for the double layer, and if we use some metal, if we combine the metal oxide and with the porous materials, or combine the conductive polymer with the porous materials, we can get these hybrid capacitors. And I would like to talk about the double layer capacitors because for the pseudocapacitors, we cannot go to high current density for charge discharge. But for double layer capacitors, we can go huge, much higher current intensity. And here is the traditional carbon materials which we use, such as carbon nanotube and graphene or carbon nanofibers. As we know that for these materials, that's very expensive. Probably every gram is about more than $100. If we can go lower cost, that will be better. So we find that if we use active carbon as electrode materials, the cost will be very cheap. As the last speaker mentioned, it's about $5 per kilogram. And so based on the idea that we won't find the lower price capacitors, we already know that corns can produce ethanol for the ethanol industry. But what about the residues from this industry? We won't use this DDGS as a source for the supercapacitors. But how we can connect this DDGS with the energy market, this is very interesting. As we know that DGS can be pyrolyzed, and we get biofuels just like gasoline, and it will directly go to the energy market. What about this? If we activate this biochar and even modified by some chemicals, we can use these three kinds of materials as electrode materials for the supercapacitors. We want to find out which one is the best. So firstly, we test the materials, use the BT surface area, it's macrometrics for test the surface area and pore structure. And here I will show you the results. For the biochar, as you can see that it's a very lower surface area. But for the active carbon, it will go up to more than 100 times than the traditional biochar. And the volume also very high. For the macropore and mesopore, it's both very high. After we modify it with the hydrogen peroxide, it go up than the traditional active carbon. So we tested the scanning electron microscopy. We found that there's some kind of, this is the active carbon SEM image. We found that there's some kind of fibers in these materials. We think that this is probably the best, the good material for the supercapacitor. So we continually tested the Raman spectrum, and we see that this is a D band. D band means disordered carbon materials, and this is G band means graphitized carbon materials. And we find that G band is kind of like more than D band, so which means for the active carbon materials, it's kind of partly more than halfly graphitized, so it will increase the conductivity of the material. And continually, we test the electrochemical properties of biochar, active carbon, and modified active carbon. As you can see here, in the lower carbon density, the voltage will drop sharply. It means there's a very huge resistance in the supercapacitor systems. And when we continually increase the current density, that's even the voltage will drop sharply, and it means these materials cannot be used as supercapacitor materials. And this is the cyclic voltammetry test. This one uses a very small scanning rate, and it looks like not very good for the this CV curve. And when we increase the scanning rate, it shows much worse than the small current density. And here we also tested the activated carbon as the electrode materials for the supercapacitor. For the lower current density, it shows a good curve. But when we increase a little bit of the current density, we can see here it's from 230 to 200. It means it will the specific capacitance will drop sharply, and when we increase to the nearly 600, there's a little drop here. It means the system contains a higher resistance, and also for the CV curve, when we use a small scanning rate, it shows looks like a good rectangular shape. But when we increase a little bit of the scanning rate, the shape will become not that rectangular. And when we continually increase, this shape is not, this is not good for the supercapacitor. And continually we test the electrochemical properties for this material. And as we can see, for all of this current density, the curve looks very good. And there's no IR drop here. And we look at this. We use a higher scanning rate for these materials. It looks very good shape. And we continually increase the scanning rate to 200. It also looks very good. That means this material is the best for the supercapacitor. And also we test the electrochemical impedance spectroscopy. And we find that biochar, as you can see here, the semi-curve means that it's the inner resistance of the system. And we can see that biochar is about, it's around it's the highest. And for the modified active carbon, it's very small. It's about just less than 1 ohm. So based on all of this tests, we would like to say that biochar does not show good properties for the supercapacitor. And the active carbon presents higher specific capacitance, but it cannot go very high current density, so it's not good for supercapacitors. But for the hydrogen peroxide modified carbon, it shows higher surface area, and also it shows very good CV curve, and it also shows the lowest inner resistance. And finally, I would like to thank you for USDA and NIFA. And I also would like to thank you for Dr. Gu and Joe Pauling and Wendy. Thank you for your attention. That's it.